so our next speaker is Jenny August from MPI Bonn, and she will talk about silting and tilting theory for weakly symmetric algebras.
Okay, thank you, Johanna, and thank you very much to the organizers for this lovely event and giving me the opportunity to speak. I'd like to use the short talk to tell you about a short paper that I have that's joint work with Alex Dugas, which is titled The Silting and Tilting Theory for Weakly Symmetric Algebras. So I want to start off with a quick reminder of tilting and silting theory. So A is going to be a basic finite dimensional algebra throughout the talk. And over such an algebra, a perfect complex is called tilting if two conditions hold. First, that there are no morphisms from T to any non-trivial shift of T. And second, that the thick subcategory generated by T is the entire category of perfect complexes. And silting, as you probably know, is a generalization of this, where we only alter the first condition and ask that there are no morphisms from T to any positive shift of T. So negative self-extensions are allowed. So tilting and silting, they're both very well studied concepts. So tilting dates back to Ricard's work on derived equivalences. And in fact, due to his work and perhaps also work of Keller, tilting and derived equivalences are essentially synonymous. Whenever you have tilting, there are associated derived equivalences. If you have derived equivalences, there are tilting complexes. But there are also reasons that you might want to study the more general notion of silting complexes. One, due to Ehara and Iyama, is that silting complexes have a much better behaved notion of mutation. So whenever you take a silting complex, you can mutate at any indecomposable summand, and you can iterate this mutation and produce lots and lots of silting complexes from a given one. Another reason that you might want to study silting is that they have a very strong connection to the bounded T structures of the derived category. And this was actually the original reason they were introduced by Keller and Wozniak. However, silting complexes do have the disadvantage that if you're silting but not tilting, you don't necessarily have a derived equivalence, at least not one to a normal algebra. And this can actually make them more difficult to work with. So a really ideal situation is actually when all the silting complexes of your algebra are tilting, because then you can use the advantages of both. So you can use the mutation of the silting complexes, but also the derived equivalences coming from the tilting. So the question is then, for which finite dimensional algebras are all the silting complexes tilting? So this is very well known if you have a symmetric algebra. So by definition, this is when A is isomorphic to its dual as a bimodule. But equivalently, you can say this is when the Nakayama functor of the algebra is isomorphic to the identity. So as I say, it's very well known that if A is symmetric, all silting complexes are tilting. And the question that Alex and I wanted to ask is the same true for weakly symmetric algebras? So these are just a mild generalization, where instead of asking that this functor is isomorphic to the identity, you just ask that when you apply it to a projective module, you get back an isomorphic projective module. So symmetric clearly implies weakly symmetric, but there are algebras that are weakly symmetric but not symmetric. For example, Brenner, Butler, and King show the pre-projective algebras of Dynkin type D2n, E7, and E8 are weakly symmetric but not symmetric, at least not unless the characteristic is 2. So this is our question. Over a weakly symmetric algebra, are all silting complexes tilting? So we can make some preliminary observations. So the first thing to do is look at a very restricted class of the silting complexes, so the 2-term silting complexes. So these are literally just silting complexes which have non-zero terms only in degrees 0 and -1. So a very restricted class, but also a very well-studied class because of their connection to tau tilting theory due to Adachi, Iyama, and Brighton. And so because there's lots and lots of results about 2-term silting complexes for general finite dimensional algebras, you can actually put a few of these together and quite easily see that over a weakly symmetric algebra, all 2-term silting complexes are tilting. So at least on this very restricted class of silting complexes, our hypothesis is true. There's another result that you can obtain pretty easily from the literature. So in a previous paper of Dugas's, he has a result that we can easily deduce the following from. Namely, if I take a weakly symmetric algebra, this is an algebra, so it's a tilting complex over itself. So we can carry out silting mutation on this, on the algebra itself, and iterate this, producing more and more silting complexes. And it turns out that if you start with a weakly symmetric algebra and you mutate and end up at a silting complex, this must actually be a tilting complex. And as a consequence of this, if you take a silting connected weakly symmetric algebra, this literally just means that any two silting complexes are connected by mutation. In this case, all the silting complexes are tilting. So this sort of provides evidence that maybe it is true in general. However, the result in our paper is that actually, no, it's not. So we can provide a counterexample of a silting complex over a weakly symmetric algebra that is not tilting. However, although we show that it's not true in general, we do also show that it is true if the tilting theory of your algebra is well behaved. So this is essentially our paper in a nutshell. So then I just want to give some more details about it. So the first thing is to come actually to the second result and tell you what I mean by being or having well-behaved tilting theory. So this is a property called tilting discrete, which was introduced by Ehara. And without giving you the definition, it essentially means that the number of tilting complexes can't grow too quickly. So there's somehow a bound on the number of tilting complexes. Ehara and Mizuno, they actually have some really nice characterizations of tilting discrete and also of the silting analog, silting discrete. And in fact, if you combine some of those characterizations with simply just these preliminary observations on the previous slide, you can fairly easily deduce that in fact, any tilting discrete weakly symmetric algebra is silting discrete. And if you're silting discrete, then in fact, it's well known that you're silting connected. And so all the silting complexes are tilting. So at this point, I really want to mention a paper by Adachi and Keza that came out right at the end of December. So their paper has come out before the paper of Alex and I, and actually also contains this precise result. So they get there independently, and they have a different proof. Actually, it's very interesting. It uses a concept called new stable silting complexes. But however you get to this result, you can then apply it to these pre-projective algebras of Dynkin type D2n, E7, and E8, which are weakly symmetric. And these are known to be tilting discrete by Ehara and Mizuno. And I think what's nice about this result is that it means that you only have to prove something about the tilting theory of your algebra, and then actually you know about the silting theory as well. In particular, when you're proving something about the tilting theory, you can use the associated derived equivalences, as Ehara and Mizuno do strongly in their proof of tilting discreteness. But then, using this theorem, it turns out that actually you were dealing with all the silting complexes all along. So I want to turn now to perhaps the most interesting part, and the fact that we have an example of a silting complex over a weakly symmetric algebra that is not tilting. So instead of giving you the explicit example, I thought it was more insightful to say, how do we go about finding such an example? And from the results I've already given, you can see that in fact any counterexample must come from a non-silting connected weakly symmetric algebra. And as far as I'm aware, there weren't really any explicit examples of such algebras in the literature before. But Alex Dugas has an earlier paper precisely on non-silting connected algebras. And so what we start with is one of the examples in there, namely a non-silting connected algebra it's not weakly symmetric, it's not even self-injective, but we start with this finite dimensional algebra that's non-silting connected. And along with this, there's an explicit tilting complex, which is not connected to A via mutation. And the idea is actually we can produce a weakly symmetric algebra from this finite dimensional algebra. And this uses a generalization of the notion of trivial extension algebra. So whenever you have a finite dimensional algebra, you take the semi-direct product with its dual, and this is the trivial extension algebra, which is always symmetric. And it's known by Ricard that you can always lift a tilting complex over A to a tilting complex over the trivial extension algebra. So we just use a generalization of this called the twisted trivial extension algebra, because we don't want a symmetric algebra. We want something that's weakly symmetric. So we twist by an automorphism of the algebra. And it's in a paper of Joseph Grant's that this is always a self-injective algebra. And in particular, if you can choose your automorphism appropriately, it's also weakly symmetric. So we build this twisted trivial extension algebra of Alex Dugas's example of a non-Silting connected algebra. And then, just as Ricard shows that tilting complexes lift to the trivial extension algebra, we can show that this tilting complex T lifts to a Silting complex of this weakly symmetric algebra, but a Silting complex that is not tilting, giving us the counterexample that we needed. So thank you very much for listening.